Hello everybody, and welcome to our webinar on how to build a predictive maintenance application. Before we begin, I do want to take a moment to introduce myself. My name is Logan Kraus. I am an application engineer with Sorba AI, and today I will be leading you through how to build a predictive maintenance application specifically centered around our clustering models. This is the first in a series of webinars that will go over different applications of the Sorba platform, and we'll go over different ways in which you can implement predictive maintenance using Sorba. Today, though, we'll be going over the clustering model specifically. If you could, please take a moment to answer the poll questions that will be going out right now, just so we can get a better idea about who we have in the audience. And as the presentation is going on, please feel free to ask questions in the chat, and myself or one of my colleagues will be there to answer your questions. And also, please do remember to fill out the survey that will be sent out at the end of the webinar so that we can get some feedback from all of you. To begin, let's go over what exactly Sorba is. Sorba is a machine learning artificial intelligence platform that combines the best of an IoT unified platform with the best of a machine learning platform. So a couple of things that are very good about Sorba is that it is a completely end-to-end platform. What I mean by that is, as I just mentioned, Sorba essentially combines an IoT platform that it gives you the capability to easily connect to all of your different data silos and to bring that information easily into Sorba, with a machine learning platform that then allows you to analyze that data and build machine learning models so that you can begin to make your machines operate smarter using that data in order to implement practical changes to your machine. Additionally, we operate in an entirely real-time format, so we're not taking samples of your data and giving you reports for it. What we specialize in is taking your data, feeding it into machine learning models, and giving you real-time results, whether that's with optimization, giving you set points for your machine, or in this instance with predictive maintenance, giving you a real-time anomaly detection score that will tell you what the chances are that there either is or will soon be an anomaly on your system. Sorba operates as an edge analytics platform. However, we do have the ability to deploy it in different formats. We'll go over that in just a moment, though. And the final benefit that I would like to talk about is the low barrier to entry for Sorba. Sorba is a no-code solution, meaning that you do not need to have any coding experience or knowledge in order to use the software. And because of that, from a technological standpoint, it's very easy for users to begin working with the software. And it is a low barrier to entry both from that technological standpoint and also from an economic standpoint. Before we dive into predictive maintenance, I do want to take just a moment to go over some of the other applications that we have within Sorba. Sorba also has the capability for advanced process control and optimization. We also have the ability to do digital twin and forecasting. And then we also have specialized applications for vibration analysis and for OEE. So with that, let's go into predictive maintenance. Oh, sorry, actually before that, just to take a brief moment to talk about how Sorba is actually put into place within a facility. So we have essentially three different ways in which we can install Sorba. We can either install it as a physical edge device, where Sorba is implemented through an edge computing device. We can also put in Sorba as a virtual machine on the plant network, or we can do an entirely cloud-based solution. And here we have the required features for Sorba. You need 8 CPUs, 16 gigs of RAM, and so on. And in general, we recommend that you have at least 2 engineering users who are using Sorba through a virtual desktop, and then 1 admin with access to the SDE. With that, let's move into predictive maintenance. And before we begin, I do want to just take a brief moment to talk about what exactly PdM is, and also our approach to PdM with Sorba. Predictive maintenance is essentially an alternative to preventative maintenance, where instead of fixing your machines and performing maintenance on a set schedule, you instead perform just-in-time maintenance, performing maintenance only when it is actually required for the system. So, with Sorba, the way that we actually accomplish that is by building machine learning models that can tell you when there are or will soon be issues with your machine. So here we have your current system where you have the process, whatever asset you're trying to perform predictive maintenance on, connected to some form of PLC and typically connected to some form of a SCADA system, OPC server, or some form of data historian. We then have Sorba. We take that data from the historian, from the OPC server, or if we need to, we can take it directly from the PLC, and we bring it into Sorba for our data acquisition and real-time control. That data is then brought into Sorba's historian, and then from there we do essentially a couple of things with it. That information can then be visualized using our dashboard designer, and that information can be brought into the machine learning trainer so that we can build a machine learning model in order to perform predictive maintenance with this data. And then once the machine learning trainer generates that model is then deployed into a real-time setting where it can then be giving you at every moment what the current chance is that there is or will soon be an anomaly on that system. And that information can then be sent back towards the machine, or it can be visualized within Sorba. So today I want to go over what problem we'll be tackling. We'll be doing predictive maintenance for a variable frequency drive. A VFD is a type of motor drive that controls the speed by varying the frequency of the electrical input. For this application, we'll be collecting these tags: current, frequency, speed, power, torque, and voltage. Our goal is to use this data that is being collected by the VFD in order to create an anomaly detection algorithm that will then tell us when the motor is experiencing an anomaly, and typically that anomaly would be related to some sort of failure. And before we go any further, I do want to talk a little bit about what exactly a clustering model is, as that is going to be the focus of today's webinar. A clustering model works by identifying clusters of data. This helps to then identify different normal operating conditions for the asset, and then when the data falls outside of those clusters, you can consider that to be anomalous data. So right here we have this cluster and this cluster that represent different operating conditions for this system. This right here would be representative of a two-variable system, and the reason why this sort of approach to it is better than traditional methods for identifying anomalies is because it is not just looking at the actual ranges for the data, it is also looking at the relationships between the different variables. What I mean by that is that for variable x here, if we have a data point right here, that is fully inside of normal operating range for variable x, and that data point right there is fully inside the normal operating range for variable y. However, that data point would fall outside of the two clusters of behavior that have been identified, and so that data point would still be considered anomalous. Classification is a little bit different. The way the classification works is by labeling one of the clusters here as the one that you're trying to identify or the one that you're trying to classify. What that does is then it doesn't tell you when there is any anomaly on the system, it tells you when you are experiencing that particular anomaly. And that can be very, very useful for, if you have a failure on the machine, being able to then tell when that particular failure is going to happen again. We'll be going over classification in more detail in a future webinar. For today, though, we'll be going over clustering models, which are also used for anomaly detection and are just essentially for general anomaly detection, where they will detect anything that you do not define as normal behavior. But it will not give you as much information about what specifically the anomaly that it's identifying is as compared to a classification model. The first step to carry out our predictive maintenance application is to set up our data collection. In order to do this, we must first determine the data source, configure the channel in our IoT Unified workspace. We then must set up the asset, group, and tag structure within this workspace, and then we will verify the flow of good data. So, in order to do that, let's move over into our SDE. This is what the Sorba Edge looks like. In order to access your workspace, go to the Workspace tab right here. You will then have your device. Here you can configure all the device settings for your Edge device. And then within that device, you'll have this drop-down for your assets. I've already created a motor asset here. We are going to now create a channel in order to connect to an OPC server. To do that, I'm going to add a channel. I'm going to call this OPC. And I am then going to go ahead and select OPC UA. You'll notice that there are many different drivers here. This is to connect to all sorts of different SCADA systems, OPC server, PLCs, whatever you're trying to connect to within Sorba, you can connect to using the associated driver. Now, for an OPC server, we need the OPC UA endpoint. So you can see right here that we need the IP address and the port for our OPC UA server. So for this, opc.tcp 192.168.1.152. And of course, this is going to vary depending on the IP address for your specific OPC server for the device that you're trying to connect to. You also have here the information for your security policy as well. If you do not have a security policy set for it, though, you can go ahead and click Save for your channel. Once we've created the channel, we will see that it is not currently loaded. And actually, if I were to apply changes right now, this would actually show up as an error since we do not currently have any tags associated with this channel. So I'm going to go ahead and create my first tag. So as we mentioned, we need to set up our asset group tag structure. Tags are the most basic level of information within Sorba. They represent an individual variable on your system. They are essentially one piece of information. So there are things like the current, the frequency of the motor. They are the different variables that make up your system. Groups and assets are a little bit more vaguely defined because they really depend on the specific application. In this particular instance, we have our motor as our asset. Then we're going to have one group for our real-time tags, and then we'll likely have another group for the outputs of our machine learning models once we have created a model. For the moment, I'm going to go into this example group that I created, and I'm going to add a tag. I'm going to go ahead and call this tag 1. Here, I'm going to define it as a real value. You can set a default value for your tag here. If Sorba does not get any information for the tag, it will go to that default value. And you can also set any pre-processing parameters that you want right here. You can also set the low and high limit right here for the tag. And this is where you control how often that data is being collected. So this tag I'm going to leave on cyclic 10 seconds, meaning that this tag is going to be collected once every 10 seconds. However, you can also use raw time. You can use on change, which is particularly good for Boolean values, as well as rising and falling edge, which is also good for Boolean values. Always, which is just going to collect the data as quickly as it possibly can, or based on an event trigger, which is going to only collect it if another Boolean tag is triggered. All right. So again, though, for this, we're going to leave it on cyclic 10 seconds, and then we select our channel. If you leave it on a memory channel, then it is just going to be stored internal to Sorba, but we, of course, want to connect this to our machine. So we're going to go ahead and use that OPC channel that I created. You can set the access type right here. So for this tag, I just want to take information off of my OPC server. I don't want this tag to write back to my OPC server, so I'm just going to set this to read only. The access type is also defined here. And then I need to put in the OPC tag name here. So for this, I need the actual specific tag name for this tag off my OPC server. I'm going to, however, use discovery. So I'm going to go ahead and use this discovery right here, and this is going to give me a list of all the tags on this OPC server. We'll give that just a moment to run. There we go. And now we can see here that this is going to show us all the different information on our OPC server. So I can go ahead and find my tag 1 right here that I was looking for. And here's where you would set the OPC data type. All right, once that is done, we can go ahead and save and apply changes. And we're going to give that just a moment to run. While that is running, I want to go over quickly. I already have set up, just for the sake of time on the webinar, our real-time tag group with all the tags that we're going to need for our example today from our VFD. So for that, we have current, frequency, power, speed, torque, and voltage. And this is all the information that is coming off of that VFD. Here we have settings applied successfully, and let's go ahead and refresh this. Oh, and of course, that information is not being pulled from this OPC channel that I just created. The information for our RT group is being pulled from this motor data channel. Now we can see that it has changed to running, and we have a tag connected to it. But how do we verify the flow of good data? For that, we can use the data view within Sorba, which is located right here. And here is going to have our asset group tag tree structure. So we can go into our motor asset. I did this in the example group, and I can see tag 1 right here. It is on polling mode right now. Let's go ahead and run this. And I can see that I have data for this tag, and it is updating. All right, and just to check, just to make sure that everything is still working for it, let's go ahead and check on our real-time tag group. We can see right here that we have data for all these tags, and they are updating as well for all this information that is being pulled off of our VFD. All right. And that is how you set up the data collection. After we have verified that our data collection is good, we can then move on to model creation. Now, I am skipping a little bit of a step here, which is the data collection step. So once you have set up your data collection and ensured that the data is flowing properly, you would then typically wait 1 to 2 weeks in order to allow the model time to collect information from your asset before actually trying to create a model. This can be accelerated if you have historical information. You could bring in that historical data set into the machine learning trainer in order to bypass this waiting time. So, in order to create the model, we follow these steps. We create a data set within the machine learning trainer. We create a project and our analysis. We verify good performance of the model, and then we deploy our model. So, for this, I'm going to go back into my SDE. In order to access our machine learning trainer, we go right here to our ML trainer. From here, we can go ahead and create our data set. I'm going to make a new data set for my motor data. And then here we select our source. So if we're using hot data, which is typically the most common one, we're then going to go ahead and select the asset, which in this case is the motor. Here we select our time range we want to pull information from. And then we are very simply going to select which tags on that asset we want to bring in to our model. However, I just created this asset and I just created this these tags that are collecting data, so there currently isn't enough data to create a model from, which is very similar to what you would experience in a real application. So in order to bypass that, we can actually use a CSV file as our data source, and then we can bring in an external CSV file to accelerate this process by bringing in a historical data set for this machine. So I'm going to go ahead and select my file. There we go. And then you're going to go ahead and select your date field. In this case, it is timestamp. What this data file should look like if you're bringing in an external CSV is simply the data in rows with a column header for each of the different variables that you're collecting, and one column that is your timestamps. And here is the date format. It should auto-detect it, but here is a list of all the acceptable date formats within Sorba. And you set your time zone here. We'll then select from that data set which of the different fields, which of the different variables that we want to include in our data set, and we'll select what we want to do for data cleaning. So when you're creating a machine learning model, it's important that you don't have any holes in your data. You can't have null values. So this is what you're telling Sorba to do when it finds a null value in the data set. If you set it to discard, then if there is a missing value for the current at a certain timestamp, it will discard the entire row of data. This is the default option. However, if you have a lot of holes, or if you have one particular tag that has a lot of missing information, then that can remove large sections of your data. So there are a few other options for how the data is cleaned. You can replace with the mean value for the tag, so that's simply going to replace with the mean value for the current if it finds a hole. You can replace with a set value that you would set here, or you can replace with the previous value, which is just going to use the last value that it had for this variable. For the moment, I'm going to leave this on discard. You can add in extra features here. This is to add in extra calculations. So for instance, let's say you want to add a moving mean for the current, you would do that here. And here we can set filtering. So if you want to add in a rule, such as, for instance, let's say I want to make sure that the speed is greater than, and you can actually compare it to another tag or to a numerical value. So let's say that I wanted to add a rule that the speed is greater than 0. I could do that here to make sure that I'm only bringing in information when the motor is on and functional. What this is going to do is it's going to filter down the data, so it's going to remove any times when this condition was not met from my data set. And here we have extra processing options. So this extra processing takes slightly longer when you're generating your data set. However, if you select these options, it will then run correlation, data quality metrics, a tag ranking, and data drift calculation. You can also allow for filtering based off of these. In order to turn them on or off, just click on the box. I'll leave them all on for the moment. And you can actually see the filtering right in here. I'm not going to go through all these, but for instance, if I wanted to filter based on correlation to get rid of values that were highly correlated with each other, I would change this to yes, and then I would set the correlation value, at which point when it crosses that threshold, it will get rid of one of those values in order to avoid having values that are highly correlated within your data set. And with that, I'm going to go ahead, and I'm actually going to turn these off and just leave these on because these take slightly longer. I'm going to go ahead and save my data set. Before I do that, though, you can preview it here. This is just good to make sure that you actually do have data within your data set and to make sure that you're not bringing in an entire empty column or something like that. I'm going to go ahead and save this data set. It is creating right now. And as it's creating, we can actually see right here the status of it. And this is going to show us the steps as they're completed for this data set, so that way we can track the progress and see if anything goes wrong at any step within this. All right, and the job is completed. With that, you can then go into your data set and you can go to this Explore feature. And here you actually have a lot of information about the data. So you have a summary of your data. You can see the trend lines for all of the different variables you're bringing in. You have a scatter plot. You can set this to either be a 2D scatter plot, and you select your X and Y axis here. And you can also add in an additional axis on your Z axis here and set this to be a 3D scatter plot as well. You can see box plots for all of your data here. You select here which ones you want to display on the screen. You can see a histogram right here. You can see a parallel coordinates plot here, which essentially for this, you can look at the different values on your system, and you can actually highlight a section of your data on any of these. Froze up on me for a second. Let me reload that page. There we go. So I can highlight a section of my data to see these lines going from value to value in order to track how the different variables within the system relate to one another. So essentially I can see if my current is low, that typically leads to high frequency values, and it leads to high power values compared to the other ones, and high speed values. So you can kind of see here how different ranges of values for one variable relate to the ranges of variables, to the ranges of the other variables within your system. And here we have correlation and data quality because we chose to run those ones. If you choose to run tag ranking and data drift, there will also be tabs for those as well. Here we can see the correlations between our variables, and on data quality, we can see our data quality metrics. We can see which ones had outliers, and we can also see a count of how many outliers there were. Once we have our data set created, then we can go ahead and create a project. For this, we can either go to the project section within Sorba, or we can simply go to our data set and create a new project from that data set. So here I'm going to go ahead and create my motor project, and you can see it is linked to my motor data set that we just created. All right, and from here I'm going to go ahead and create a new analysis. I'm going to go ahead and call this clustering. And here I'm going to select which tags I want to bring in. In this case, I want to bring in all the tags on my system. And you again have the option to add in extra features and advanced rules at this stage. There is one difference on the advanced rules at the project stage compared to the dataset stage, and I do want to point this out. On this one, when you create a rule for it, you can choose whether you want to include it in training, include in the runtime, or both. If you choose to include in the training, then it will filter according to this rule. If you choose to include in the runtime, then when this model is deployed back into a real-time setting, it is going to only be running the model when that condition is met. So, for instance, if I put in some sort of variable that is indicative of whether or not the machine is on, that can prevent the model from running when the machine is idle and not actually running. So that way you can avoid having it give you false anomalies when the machine is off. All right, and with that, I can go ahead and select Next. And here is where you select which algorithm type you're using. So again, clustering classification related to predictive maintenance. Then we also have regression, optimization, digital twin, and forecasting. For this, we're going to go ahead and select clustering. And then we can go ahead and select which specific algorithm we want to use. For each of these different algorithm types, Sorba gives you access to a suite of different machine learning algorithms, or you can leave it on auto select. Auto select is going to look at the data that you're putting into Sorba, and it is going to select which of these algorithms it thinks is the best match for your data set. You also have access to advanced settings here if you have more of a data science background, where you can set everything from the downsampling to the pre-processing algorithms to the dimensionality reduction. Or you can, of course, if you're less familiar with that, just leave it on auto select for your selected algorithm type. Every algorithm type has an auto select feature on it, and we can carry on. Here we select which versions of the data set we want to include. If I have made multiple versions of this data set, I could select which ones I want to bring in, but of course I only have the one version that I just created. And from here, I can go ahead and create my analysis. Now our project is being generated, and we can see right here, again, the status on this to see our model being created and to see as those steps go on. And of course, here we'll also see if there are any errors when it is being created. All right, it should be almost done here. I do want to point out that for this, I'm bringing in a relatively small data set for the sake of time. This training time is variable depending on how many variables you're bringing in, which model type you are trying to create, and also the length of time that you're bringing in. So how many samples are you bringing in? So this can range from anywhere from a few seconds to a few minutes to, in some cases, for large complicated data sets, it can take a few hours to train, but it really is dependent on a lot of factors. All right, and job completed successfully. Our model has been created. From here, we can go ahead and explore our model. And here we can see it is similar to the last one. We do have here our anomaly detection one. We can see that within this data set, actually it detected 2 anomalies within our system, here and here. And we can also actually go up here to check the properties on our model, and we can check our performance score for this model. So here we can see that we got a score of 0.94, which is a very good score for this. So this score for the clustering model ranges from 0 to 1, and we typically want it to be at least 0.8, preferably 0.9, in order to put the model into production. This score is essentially telling us how confident the model is that it can accurately predict anomalies on the system. So if this score is not good enough, then that typically means that you simply have a too small of a data set, or you are bringing in variables that are not indicative of the actual behavior of the system. In the first case, that's an easy fix. Wait another week, collect a bit more data, and try running your model again. In the second case, if you don't have indicative data, then that might mean that you need to bring in more data into your model, and by that I mean more tags. So essentially what I mean by this is there are some tags that are very representative of the system, and there are some tags that don't really give a good view of how the system behaves and how it operates. So you may need to bring in more information that is more indicative of the actual operating conditions of the machine. All right. And one other thing that I want to mention before we move on here is the tag ranking. This tag ranking is showing us how heavily each of the tags that I brought in contributed towards that anomaly detection curve throughout the entire time. So here we can see that the voltage actually was the highest contributor towards the anomalies that were found within this data set, followed by power, followed by speed. And this is actually quite a useful tool, but it is even more useful once we deploy it into a real-time environment, because this tag ranking is carried forward into the real-time environment as well, and we can see in real time the contribution of these tags towards the current anomaly score. But we'll go over that when we get to our visualization section. All right. And the next step from here is to deploy our model. So to do that, we're going to move back into our IoT Unified workspace. In order to deploy our model, we're going to go back to our motor asset, and then we're going to go to model instances. Here I'm going to add a new model. I'm going to put in the name for it. I'll put it in as clustering. And then I select the project that I am pulling from, the analysis that I want to use, and the specific model number. It will then bring in all the info for that model. And here's where you can set up auto learning. So auto learning is a very useful tool within Sorba. It enables you to have a model that is consistently improving upon itself and learning and adapting as your machine changes over time and as more data is collected. In order to use auto-learning, you do need to have a Boolean tag set up within your asset. You would select which tag that is here. When that tag goes to true, then it is going to trigger a retraining of the model. You set here the time range that you want it to retrain on. You can either set it to the last X number of minutes, a specific range, or you can just set it to retrain from the last time that it was trained. If you select this, it will keep all these auto-learning parameters on the new model so that it will continue to do this as you update the model over time. Here's if you just want to keep the same model settings. Here is if you want to either keep the model and just disable it, or if you want to fully delete the old model. I typically recommend just disabling it, so that way you can always roll back to an older model if you need to. Here you select the option for if you want to roll back automatically if the performance metric for the model is worse on the new one than it was on the old one. And here you can select which versions of the dataset you want to include in this retraining. All right. Here we can select if we want to automatically generate a dashboard in order to visualize the information from this model. And then here we have our inputs and outputs. So it's going to try to map the inputs to the ones on my system. I can see here that it is pulling all the correct information for my input tags for this model. My output tags, I have nothing created. So what I can actually do to accelerate this process, instead of making these tags all manually as memory tags within Sorba, I can just suggest a new mapping, go to my outputs, and then click here to generate to automatically generate tags for all of the outputs from my anomaly detection model. I'm going to go ahead and create those tags. And those tags have been created, and I can see now that they are updated right here. And with this, I can go ahead and hit save. All right, and I'm going to apply this. And we will just give that a moment to update. All right. And once this updates, we should see it go from not loaded to loaded. And there are a few things I want to talk about on these outputs. In particular, I want to talk about the anomaly score. This score is going to be giving you, once this model is fully deployed, which it will be in a moment, it will be giving you in real time the current percentage chance that there is or will soon be anomalous data on the system. And we also can see here that we have the tag ranking that I mentioned before. This tag ranking is telling you how heavily each of these different variables is contributing towards the current anomaly score. So it said that it finished the apply, so let's go ahead and refresh and make sure that our model is actually running. And there we go, it is running. And let's just check on our data view real fast to make sure that it is actually giving outputs. We can see here that it created a new group for this model with our outputs in it. And let's just check our anomaly score percentage. We can see that we currently have a value and it is updating. All right, and that is how you deploy your model. And with that, we have completed the model creation stage of our project. From here, we can move on to our final step, which is visualization of our data and notification. For this, we need to create a dashboard to visualize our data, and we can also set up external notifications in order to track anomalies outside of Sorba. So, back to our SDE here. We're going to go to our workspace, and if you remember, when we deployed this model, we selected for it to automatically generate a dashboard associated with these outputs. So we can actually click on this right here to open a dashboard designer. And this will bring us to our dashboard designer. And here we can see, I'm going to set it for the last 5 minutes, our current information for this model. So here we can see a state timeline of our anomaly score. As we can see, we do not have any anomalies currently. We can see the current anomaly score for our model. And we can also see our current tag ranking. So for this, it's showing us at this moment, we have this anomaly score, and this is how heavily each of the different tags on our system are contributing towards that anomaly score. Now, when we're not experiencing an anomaly, this information isn't particularly useful. So as you can see right now, we have an elevated current tag, but we're not experiencing an anomaly on our system, so that information isn't really all that valuable. However, when we actually have an anomaly on our system, then this information on the tag ranking can actually be used in order to start root cause analysis. It's not a absolute, one stop for root cause analysis, but based on the tags that are elevated when we have an anomaly, we can start to get some idea of what might be wrong with our system. For instance, let's say that we have the current tag elevated and we have the torque tag elevated as well. When we have an anomaly score, that can mean that there's some form of mechanical issue that's causing an increase in the torque and it's causing it to draw extra current to the motor. So maybe some sort of additional friction on the motor is causing an issue with it. So based off of those tags, you can kind of start to do root cause analysis to figure out what is wrong with your system. Now, the other aspect of this is to set up notifications for when there is something wrong with the system. To set up notifications, we're going to go back into our IoT Unified Workspace. First, we're going to go ahead to set up an alarm. To do that, go to your alarms within your asset and add an alarm. Put in a name for that alarm and a message. Then you're going to put in the rule that you are checking for with this alarm. So I am checking to see if my anomaly score percentage is greater than 80. And I can see my complete expression here. And you can also link this to a notification channel, which we'll get to in just a moment. I can save this alarm, and now within Sorba, it's going to give me a notification whenever the alarm is triggered, which will, in this case, happen when my anomaly score goes above 80%. Now, there are a few ways in which you can set up external notifications. You can use the script engine or the workflow within Sorba to send out notifications. You can also set up a notification channel. To do that, you're going to go to the notification nodes and add in a notification. From here, you put in the name for that channel. And then we're going to go ahead and select if you want to send out email, text, Slack, or Teams. And for each of these, you'll then have, for instance, on email, the email provider, and then you'll have the information from the email provider to put in to set up that notification channel. For Slack and Teams, it's just going to be a webhook, and for text, it is sending through a Twilio. So that can all be used in order to send out external notifications. So going back to our alarm, as we can see on this, if we have that set up, we can actually link that to a notification channel, and then we can have it notify us when the alarm is activated, deactivated, and or when the alarm is acknowledged within Sorba. So we can set that up in order to tell us when any of our alarms have any activity on them. In addition to that, we could also actually send this information as a tag. We can set the tag to, instead of being read-only, we can set it to be a write tag, and then that tag can be written back into the SCADA system so that way operators can view it in a real time. And the final one that I want to touch on quickly is we can make a dashboard node. So I'm going to go ahead and import from Dashboard Designer. From here, I can go ahead and find my model that we created a dashboard for. It was called clustering. Let me see if I can find that real fast. Here is our clustering model. Yes. So clustering anomaly detection. Going to go ahead and import that so we get a node for it. And then within this node, I can actually go ahead and set up dashboard reports. And from here, I can set a schedule for sending out dashboard reports. And what that's going to do is it's essentially going to send through the notification channel that you link it to. It is going to then send a screenshot of that dashboard for the selected time range to that notification channel. So those are the different options that you have for sending out external notifications. Again, you can set up dashboard reporting. You can set up notification channels to send through email, text, Slack, or Teams. And you can also use the script engine or the workflow to send out email notifications, or you could just simply write the tag back into your SCADA system so that an operator can view the information in a real-time format. So depending on what you want to do for your specific application, that is how you would set up external notifications in order to track your anomalies when they occur. With that, we move to the next steps. So at this point, you have your predictive maintenance application, you have created a clustering model for it. What are potential next steps? So a clustering model only detects when anomalous behavior is present on the machine. Classification models are very useful because they can categorize when specific anomalies are occurring. What I mean by this is a clustering model is going to look for any form of an anomaly in your machine. A classification model is looking for specific anomalies. So if you have historical information for specific failures that have occurred in the past, it is very good to then set up a classification model for a different classification model for every single failure that has occurred on this machine, because then you can start to build a library of different classification models to identify when those failures are going to occur again. Additionally, you can add in elements such as vibration analysis or current signature analysis using the vibration application within Sorba in order to expand upon predictive maintenance and to get better predictive power by using those tools. And of course, the ultimate next step for this is to template out your solution. So using Sorba, you can actually create classes from your instances, and then you can deploy these classes out as new instances to essentially have a template for this solution that you have built, so that you can then replicate it out to all of your machines that have very similar data tag structures for those machines. And that will conclude today's webinar. Thank you all so much for attending. If you have any questions, then please feel free to ask them now in the chat. Or if you have questions that require a little bit more in-depth discussion, please feel free to reach out to me. My email is on the screen right now, lkraus@sorba.ai. Please reach out to me after the webinar, and I will be happy to answer any follow-up questions that you may have. Thank you all again so much for attending.